Hi everybody, on 1 Minute Math today we're going to do the full-length explanation of how to find the domain of a function. This would be an Algebra II or Pre-Calc context, possibly a very advanced Algebra 1 class. We're just looking at algebraic functions. I'm not looking at exponents, logs, or trigonometry, just algebraic things like polynomials, rational functions, things that might have absolute value or square roots in them, okay, that sort of thing. This is the sort of function we're looking at today, and the question is, how do I know what are the possible x values that I can put into my function? That's what the domain asks. When we ask you for the domain of a function, we're asking, can you find the set of all of the possible x values that I'm allowed to put into this function to use as my x value in this function? And the good news in domain land, usually domain and range go together. Range is going to be kind of a pain in the kazoo when it comes to this, but domain, there are very, very few cases where there are numbers that I can't put into my x value. So in particular, all those polynomials, they're going to have a domain of all real numbers. Absolute value, any kind of power function, that's going to have a domain of all real numbers. The only two kinds of functions that we have to care about when we think about restricting the domain of a function would be rational functions, a function that has a fraction in it, and radical functions. By that I mean any kind of function that has a square root in it. Okay, or any even-powered root, to be fair. A radical function would be any function that has a power in it at all. The ones we're going to care about have even powers. By and large, that means square roots. So let's take a look at these both separately. Rational functions, let's do that first. Rational functions. So my example was just the classic 1 over x. One way to think about the domain of a function, by the way, is to imagine, I'm going to draw my graph here. I'm going to graph 1 over x. Okay, and now I'm going to imagine shining a flashlight onto my graph. Here's my flashlight. And any part of the x-axis that gets a shadow on it is going to be considered part of my domain, because that's saying these x values are corresponding with a point on the graph. And this flashlight, by the way, I'm going to shine it from the top and I'm going to shine it from the bottom, and I can see that every point on this x-axis is going to get some kind of a shadow on it, except the origin right there, x equals 0. And that's why x does not equal 0 is my domain. That's my whole domain. All real numbers but 0. You might have to write that this way. If your teacher asks you to use interval notation, this is going from negative infinity to 0, and then 0 to infinity, not including 0. I know it's not including 0 because I use those kinds of brackets. If I wanted to include that number, I would use those square kinds of brackets. Yeah, logically this makes sense because I know I can't divide by 0. Right, 1 over 0, no, that's not a thing. So 1 over 0 is not defined, that means x can't equal 0, and that's why when I think about rational functions in general, let me take another one over here, what really matters is what's in the bottom. I could have anything I want up here. And when I'm looking at this rational function and I'm asked the question, what is the domain, I ignore what's on the top entirely, and I just look at the bottom and I say what can't be in the domain is the thing that makes the denominator 0, because I may not divide by 0. That's how we get the domain. Just make the denominator not equal to 0. Now that's easier said than done, because sometimes we're going to get functions, what have I used so far? H. Sometimes we're going to get functions, I'm just going to use one up here, where we have all kinds of things down here. I'm going to put a plus 7 on the end. Don't worry about that plus 7 on the end. Don't worry about anything on the top. All we care about is what's on the bottom. But I'm still asking the question, what would make this denominator equal to 0? And then those are the numbers that I have to exclude. Hopefully your algebra senses are tingling here and you realize we're going to have to do some factoring. And in this case, my domain would be x cannot equal 4 or negative 3. If I was going to write that in interval notation, I'd go negative infinity to negative 3 to 4, and 4 to infinity. Sweet. Just take whatever's in the bottom and make sure it doesn't equal 0. Similarly, in radical land, let's take some radical functions. And we're just going to start with square root again. I'm going to go back to f of x. F of x equals square root x, and let's use that strategy of putting my flashlight on my graph here. So here's my graph of square root x, and if I imagine I'm shining a flashlight down from above, and I want to ask, what part of my x-axis gets a shadow on it, it's going to be everything here. All of this positive stuff, including 0. Nothing over here, no shadow on the left, but over here on the right-hand side, all of those positive values of x give me shadow, and therefore x greater than or equal to 0 is the domain of my function. And again, logically, that makes sense, because if I ask for the square root of a positive number, even if it's a fraction, I get an answer. It's only when I go into negative land that we freak out a little bit, okay? And the square root of 0 is a thing. 0 squared is 0, so the square, I can include 0. If I were going to write my domain here in interval notation, I would have that square bracket on 0 because I want to include the 0. If I put something under that square root that is different than just x, so now let's say I had g of x, trying to change the color here, it's not taking, there we go. So I have g of x equals, and I'll put a negative 1/4, why not, x plus 5 minus 17 and 1/3. Okay. Just like over in rational function land, we're not going to care about all of this stuff. We're not going to care about any of that stuff. All we care about is what's in our important part of the function, the toolkit part of the function, or the parent part of the function, if you want to think of it that way. And in this case, it's the x plus 5. I cannot take the square root of negative numbers, so I need x plus 5 to be greater than or equal to 0, and that's how I get x is greater than or equal to negative 5. Bam. Easy peasy, right? The last thing I'm going to show you here is what happens when we put a quadratic or some other kind of non-linear junk inside my square root. And I'm going to take a pretty scary one here. I'm going to throw in, let's see, I'll make the factoring the same as our last example, but I'm going to throw in an extra x just for funsies. All right. So, as we did before, our algebra instincts are kicking in. I know that I want this ridiculous cubic polynomial expression to be greater than or equal to 0. Something in my gut tells me I have to factor, right? I'm going to let those algebra instincts take over and factor this puppy out. And I've got x times x minus 4 times x plus 3. But now here's the difference. Over here in rational land, right? We got our x values and we were like, fine, we just don't want to include those. The end. But now I'm talking about greater than or equal to 0. And that's just a little weirder. Oh, I lost my thing. Okay, I'll find it. There we go. Okay. I know that something interesting is going to happen at my 3 interesting values of x here, 0, 4, and negative 3. But I don't know what. And I can't just say, all right, 0, 4, and negative 3, they were my interesting values of x, and I just want x to be greater than them all. That's not it. Let's examine what's happening on this. In fact, I'm going to look at this a couple of different ways. You can check me on this if you would like to. I'm going to take this expression and graph just that. I'm going to pretend that I was asked to graph just that expression. If I plug that in my calculator, I get this picture. I can see here clearly that negative 3, 0, and 4, they were my interesting values of x, but where this expression is positive is between 0 and negative 3, and for x is greater than 4. And I can even test that out, right? If I take an x value that's greater than 4, like 10 cubed minus 10 squared minus 12 times 10, that's going to give me 1,000 minus 100 minus 120. That's positive, right? And I can even test, let's real quickly test what happens if I plug in 1 for x. 1 cubed minus 1 squared minus 12 times 1. That's 1 minus 1 minus 12. That is negative. All right, so this is checking out so far. The picture's telling me what the numbers would tell me if I could check all of these regions. And that's really what this boils down to. The synopsis I'm going to give you here, without belaboring this any further, is that when you have a non-linear expression, meaning it's got a square or a cube or some power on the x that's not just an x, if you have a non-linear expression underneath a radical, or in any other context, and you're asked, when is this positive? When is it negative? What you want to do is find your interesting values of x by factoring. In this case, they're negative 3, 0, and 4. divide the number line. Take all of the numbers and you're going to divide them into segments based on those values. Like those are the fence posts that will divide this fence, this giant number line, into, in this case, 4 regions. And then I've got to decide in any way that seems right to me what the value of this whole expression is in each of those regions. And it wouldn't take me long here. We've already plugged in a number greater than 4, a number between 0 and 4. If I plug in -1, I'm going to get a positive answer. If I plug in -100, I'm going to get a negative answer. Here's my fence post analysis, if you will, or my number line analysis, and I can see that the regions of the number line that are in the range that I want will be between -3 and 0 and greater than 4. Between -3 and 0 and greater than or equal to 4. Or I could have even said this: -3 is less than or equal to x is less than or equal to 0, and 4 is less than or equal to x. Okay. I hope that made sense to you. Thanks for listening. Thanks for playing along. I will see you next time.